hello again, everyone, and thank you for being here. I'm very happy to be invited in this location and this place. Great. I'm going to talk about a more applied part of the science, if you wish. So I don't know, do we have, I guess we have modelers, but do we have hydrologic modelers in the audience? Or, okay, great, and environmental modelers, like water quality, okay, and atmosphere, climate. So this is great. I hope this will make sense at the end of the day. And it's not the best thing to be between people and, of course, lunch. So I'm trying to keep it short. I'm going to talk about a little bit of the modeling that we are doing in GIWS and also some systems theory approaches we apply in our group. I would like to acknowledge, of course, Salman Razavi, who I work with, and Howard Weeder, the director of GIWS, and Brian Tolson and Luke Solis were my co-supervisors when I was doing my PhD in Ontario, Waterloo, University of Waterloo. Just mainly my talk would be divided in two parts. The first one, I'll talk about the sensitivity analysis with VARS and how we have seen the scale dependency of sensitivity analysis in different models and how we do it in a multi-criteria sensitivity analysis context. The second part of my talk would be, I will be talking mainly about the larger scale modeling in Canada. I'm going to talk about a model called MESH, introduce it, and I'll show one application in the Great Lakes Basin. So of course, I guess we don't need all of this. Why we need to do sensitivity analysis? Well, because our models get ever increasing complexity. We have a very high number of models, and they're now being used for climate change impact analysis, flood and flows forecasting, many applications. The main applications we normally look for sensitivity analysis in our models in hydrology is, well, of course, similar to many other disciplines, would be to determine what are the most important factors that control the behavior of the model at the end of the day, to characterize them and reduce the uncertainty of the model predictions by knowing those important factors better. And of course, one of the main important things that very commonly used in hydrologic modeling is to reduce the number of parameters we need to calibrate at the end of the day in order to reduce the computational cost. And there's two approaches, local, one at a time, when we change one parameter at a time, and global, as Salman talked about. So sensitivity analysis with VARS. Salman has already talked about all this. I just included in my slides because for my later reference, I have the entire picture that I needed to, but I'll just skip all this information. These are the two original papers talk about the theory and application of VARS. By the way, Salman didn't mention, but I might as well say that the VARS algorithm or approach or technique, whatever, is being now patent pending in Canada and US by University of Arizona and University of Saskatchewan. So it's in its way to be patented. And this is kind of another way of presenting VARS and sampling strategy. Just something, maybe I just add a point based on the discussions we had during the question and answer. That the sampling strategy that we use normally is very similar to any other method. So Sobol, Maurice, any other basically Monte Carlo based simulations, we use very similar sampling strategy in terms of assuming that the parameters are uniformly distributed within a defined ranges by experts, basically. And given that there is a certain pattern that VARS uses generates the samples, this is the computational cost associated with it. So depending on the number of star centers you choose, it's user defined. The number of factors is the dimension of, like, I have a 10-dimensional parameter, I have a 40-dimensional model, and delta H is basically the VARS resolution or the the smallest distance between pairs of points. So all these three factors together define how much computational cost would it take to run a VARS analysis. And this is a typical directional variogram that someone explained, and basically it shows how the sensitivity varies with the scale, and then IVARS 10, IVARS 30, and IVARS 50, which is nothing but the area behind this, underneath these curves. And then this is VARS, as someone mentioned, with one implementation of VARS, you just run it for one experiment, you get Morris, you can also get Morris indices, total order, SAMO indices, and all the VARS indices in between. So VARS is efficient. VARS, probably the main unique feature, as someone explained about VARS, that it characterizes the sensitivity across range of the scales, and it has a VARS tool, as someone mentioned. I'm going to show some of the plots, the variograms we have from a paper that has just recently been accepted. It's in press now, which we really went into seeing and exploring the impact of the perturbation scale in the hydrological models or environmental models. What I mean by perturbation scale, you can assume it is the same as delta x, delta x step size, or dx in derivative-based approaches. So when you're doing a local sensitivity analysis, changing what at a time, plus or minus 5%, you can do plus or minus 10%, plus or minus 30, and on. And what we are trying to basically say in this paper is that depending on that value of that perturbation scale, your assessment of the sensitivity of the models may change. So it is good to keep that in mind, basically. So here is one example from that paper. It's a directional variogram, a hydrogeosphere. Hydrogeosphere is a 3D fully distributed, fairly physically based 3D model, a subsurface surface flow, fairly complicated model, but I just use a very simple example with 10D. When I say 10D, I mean 10 is the number of parameters. By the way, when I say parameters, it might be a little bit different than the variables. So we have equations, the coefficients in those equations. Like if I have y equal ax, right? So x is variable in my definition, and a is the coefficient is the parameter that I change. Okay, so it is not the variable that I'm trying to do the sensitivity for. It's rather the parameters, meaning the parameters in different formulas used in my model. Which then, that's where I can fairly say those parameters used. For example, one parameter is used in the formula for calculating evapotranspiration. There's another parameter used, or coefficient used, in the formulation to calculate infiltration into the soil. Let's say parameter A2, which I can fairly assume that this is independent of the one parameter used in evapotranspiration equation. Same thing with, I have an equation to calculate the runoff. I use the coefficient there as my parameter, so that's why I can fairly say those parameters are independent. So back to the example here, I have 10 parameters I'm looking at. They are mainly coefficients of different formula used to calculate or simulate different processes in the model, like infiltration, like overland flow, like groundwater flow, and so on. As you can see here, I'm showing the variogram, the directional variogram on the vertical axis, and the perturbation scale h, or the distance between pairs of forms, and the horizontal axis. So you can see here, and someone showed some of the examples, like parameter alpha, you can see it's fairly more sensitive when perturbation scales are fairly small. And it jumps up and kind of flattens out at the end. And the other interesting thing is that you can see the other parameter HDS, which is kind of a roughness depth for the surface for overland flow. It goes here, and at about perturbation scale of 0.3, it kind of becomes more important than parameter alpha, right? So what does that mean? That if, for example, I was going to do a local sensitivity analysis with delta is equal to 30% or 0.3 of my parameter range, okay, so then I would have like find that, for example, HDS would be a more important parameter. But now that I'm able to see that basically depending on that delta X, how this parameter becomes more important and then becomes again less important at the end of the day. Again, looking at this directional variograms for various parameters, you can kind of also cluster the parameters. You can say, okay, these two parameters kind of are the most important parameters across all these scales. So for sure I can say those are most important parameters. And then you can see there's that next, the parameter NCH, beta and KS next, and then the rest of the parameters probably. So overall I can probably group them into 1, 2, 3, or 4 groups of importance basically by just eyeballing. And so there is a great deal of information you can basically obtain from looking at directional variograms, which then tells you basically how different parameters become more important or less important given a given perturbation scale. One thing again to note that so when we are sampling for VARS, we normalize all the variables between 0 and 1. Okay, so that therefore when I'm referring to h equal to 0.2, that's like 20% or 0.2 of 0 and 1. That's why it's 0.2 equal to 20% or 30% basically of the range of parameters. So this was one example. Now I want to do it. So this example that I showed was for the metric p-bias. So p-bias is a metric that is like in hydrology, you can think of it as a measure of the total volume. So you simulate your model, you want to see how much the total volume of the water during the simulation per period is how much is it close to your observed volume of the water. That's when I use p-bias. And I repeat this for different metrics. When I say metrics are basically measure the ability or the skill of the model to simulate an observed value. For example, it could be the peak flows, the high flows, or the low flows, or the total flow volume. So if you assume there is a hydrograph, a time series of flows, right? So, and as a modeler, my objective is, okay, I'm interested in flood forecasting. I'm interested into being able to simulate high flows. Therefore, Nash-Sutcliffe metric would be a very suitable metric for that purpose. And if I'm interested in also capturing or simulating the low flows with my model, then the metric I should be really looking at is the Nash-Sutcliffe of log of the flows, because taking this logarithm kind of puts more emphasis, de-emphasizes the peak flow and like more emphasizes the low flows. And as I mentioned, Pearson bias is, you can think of it of a measure of the total volume of the flow. So basically, as a modeler, I'm trying to capture, sufficiently simulate high flows, low flows, and the total flow volume. Those are what's important for me. And the message here is that depending on the metric you choose, you get a very different pattern of sensitivity analysis of your parameters. Okay, so for instance, I already showed this down here was the p-bias one that I showed, right? Which showed that maybe it is not too clear from the behind. The alpha was more important. But when I look at the Nash-Sutcliffe one, again you can see alpha is the most important parameter. However, HDS is not the second one. And the roughness, this is the famous so-called Manning's roughness coefficient of the channel that now becomes more important when we are interested to simulate the high flows. And then HDS, as you can see, it's more important first in the beginning, like in the smaller scales, but it becomes less important when you're looking at the basically larger perturbation scales. And this is the nice cycle for the log of the flows. You can see again, pretty much alpha dominates everything, and all other parameters, the rest, very insensitive or unimportant, if you wish. And this is kind of the same plot in a log scale format. Basically, now we are able to see a better kind of what's going on, especially in this area where they're all jammed together. And as you can see, they're like now for example, the roughness coefficient, whereas for nice cyclic, the roughness coefficient of the channel was the second most important parameter. Here, it's a second least important parameter, followed by the roughness of the surface. So again, the whole lot of information you can obtain by looking at these hydrographs, how parameter basically play, or their importance changes with variation of the perturbation scale, which is very nice. So if now from all these I can choose whatever the scale I want to calculate my VARS index for, but I choose VARS 50, which means I'm taking I'm now considering the entire area underneath all these curves. And that's what we call it VARS 50% of the range. And this is a mesh case study that I will be talking about later. And for that, again, as you can see, this is kind of a normalized VARS 50. That means they're converted to ratio of sensitivity. Basically, the ratio each parameter contributes to the total variation at the end. So I can, in a normalized way, so I can compare the two things. Again, you can see here, for example, this is the roughness, a sort of a roughness, a routing parameter that has a roughness component in it. For nice cyclic, it's becoming the most important parameter by far. And then S depth is depth to bedrock and drainage density. And when you're looking, this is for the high flows. When you're looking at the low flows, then the roughness coefficient or the routing parameter becomes less important. Again, you can see here S depth to bedrock is still important, but two more important parameters that we can see here is root parameters. So this is for crop, this is for grass, so different land cover types. But they're basically the same thing, root. That means when I'm looking at the low flows, the evapotranspiration, so these parameters define how much evapotranspiration occurs in my model. So now we can see these parameters are becoming more important, especially for when we're looking at the low flows. And when I'm looking at the P-bias, which is the total volume, you can see the roughness factor, which normally the roughness of the routing parameter adjusts the timing of the peak flows. That's why it's so important. But when all that matters is just the volume, not the timing, this parameter is not important at all anymore. And the roots, the drainage density, and the S depth. So this S depth is kind of the depth to bedrock, or how much you can have water inside the soil, basically. That's why it shows the volume of the water in the soil, the volume of the water that can be transpired by the vegetation. And basically, this is how much the water is drained to the system. So, long story short, depending on which metric you're doing the sensitivity analysis for, you will be identifying a different set of important parameters. So this is the same thing basically we did with multiple models, multiple criteria, the same message basically. Mesh, SWOT, and hydrogeosphere model. Metric choice has a very important influence on your sensitivity assessment. Conclusions, VARS is efficient, of course. That was an advertisement. Model sensitivity is scale dependent. By scale dependency, I mean the perturbation scale. Metric choice has a significant impact on SA. Okay, that's why. So you either have to be aligning your metric choice very carefully with your final objectives of your study. Is it flood forecasting you're interested? Is it drought forecasting? Is it flow forecasting? Volume? You have to align it very carefully. And lastly, therefore, the strategies that take into account multiple criteria and also take into account the perturbation scale dependency probably would be considered a more comprehensive and advisable way of doing a sensitivity analysis. Alright, so now I'm going to the second part of my talk, which I'll be talking about large-scale modeling in Canada for the most part. Again, you know, these large-scale models, hydrologic models, are now being increasingly used. What are some of the challenges? So, especially with Canada, representing some of the cold region processes is one of the main challenges. For example, infiltration into the frozen soil. Now it is not just a simple infiltration into the irregular soil, but soils become frequently frozen in cold regions. So we have to have a separate algorithm for that. Or snow and glacier melt in many northern parts of the Canada. Those are also very important, at the same time challenging to necessarily simulate them correctly. Representation of the natural heterogeneity, like how much really detailed information about your land cover, about your soil information, about your slope aspect, how much information you really want to add. What is the optimal complexity point? What is the spatial or temporal resolution you want really be running your model with? So those are very hot, still ongoing topics of debate, and I don't know if we can find a final best solution at the end of the day for that or not. And so another related issue or challenge with the complexity is the large number of parameters normally we're dealing with inside these models. So as they become more complex, now there's a very larger number of parameters you need to basically identify or assign a value for, which sometimes those parameters are not, they don't have real physical meaning depending on like the model you're using, or they're not measurable. So you have to use calibration. And calibrating those parameters, because the simulation takes a long time, calibration would be very computationally intensive. And, well, someone showed this page. This is the watershed systems analysis and modeling lab, someone's page. So, related to all those challenges, we are doing different activities. I'm going to talk about the largest scale watershed modeling in the cold region. And I'm talking about the mesh modeling system. So the mesh modeling system, if you wish, it's probably, I would say, the research version of the Canadian land surface hydrology model. So there is like many other places in the world, there is this tendency to do a coupled modeling system for Canada for improved hydrologic predictions. And I'm telling you, so if we have this GEM atmospheric model, all right, it just has it simulates the entire atmosphere, then it feeds into the land surface scheme to run the energy balance basically vertically, and then it feeds into the hydrologic model, mainly used for a routing purpose. Then it goes back to the oceans, and there are some ocean models that are used, and then from the ocean it goes back to the atmosphere again here. So basically they're moving towards kind of if you wish, simulating the entire hydrologic cycle in a very large scale and very physically based as much as possible. And these components that I show here, 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 or here, they can be run coupled, like together, especially these two right now, or offline, which means we run this and then save the results of, for example, precipitation temperature, and then we feed that into our models. And the mesh is basically this part. So the land surface coupled with hydrology model. So this is what we call the mesh model, which stands for Modélisation Environmentale, surface hydrology. This is as much as I can say in French. This was in French, basically. So, once again, originally this framework was introduced by Al Pietroniro in 2007, mesh, and it's, if I want to put it into context, it would be considered a semi-distributed, physically based land surface hydrological model. And a fairly sophisticated Canadian land surface scheme, which is called CLASS. So this class takes care of the vertical calculation of water and energy balance, which then connects to this hydrologic model called WATFWAT, to take care of the lateral flow of the water only. So essentially there is no lateral movement of energy sink. It's all, when it comes to hydrology, normally it's all about water moving laterally. For class, again, we need these 7 inputs: temperature, precipitation, short wave, long wave, pressure, humidity, and wind speed. So 7, which is fairly intensive, especially at larger scales. And then the way model is discretized into the mesh, when we are applying the mesh, we have to discretize the watershed into grid cells. Okay? And the subgrid variability or heterogeneity is seen by something called group response units, or it's very similar to hydrologic response units, if you have heard of it. It tries to here, if, for example, if this is one given pixel, and you're looking at different land covers, A, B, C, and D, they're scattered all over the place within that pixel, but at the end of the day, all in all that matters is the total area of each land cover. So their location within each pixel is not really important. They're going to be lumped all together, and based on the total area within each pixel, the land surface model runs, and then a weighted average of all those simulations, it's what's the total volume of the water at the end, which then will be routed by the hydrologic part within the network of the river system in the model. So the way the GRUs are defined, normally you can say, okay, it's based on the information we have about the land cover, different like crops, forests, urban areas, grass, for example. But you can also include soil information. You can include information about a slope aspect. So as a hydrologist, whatever you think is important for your hydrology, you can include that. It's a free software. It is considered a kind of community model, meaning it's free. Different people, different groups can contribute in developing it. There's a free Mesh Wiki page for it available. I applied this to the Great Lakes Basin, the Great Lakes of North America, of course. It's a 1 million kilometer square, very important basin shared between Canada and US. These are the greatest source of drinkable water, if you wish, or fresh water in North America or in the world. Surface water, I'm talking about the surface water. They're actually visible from the space. More than 20% of the world's fresh water comes from this area, and more than 33 million people in Canada and US rely on these water resources. So very important. So I basically applied this model. You can see this is the model now discretized into grid cells of 4,000 grids of 15 by 15 kilometer. And we use 7 GRU types: crop, grass, deciduous forest, coniferous forest, mixed forest, water, and impervious areas. And I use two different calibration strategies. One is called global, one is called individual. With global, simply speaking, you can see here, this is all the 5 Great Lakes. I go and, for example, choose 20 subbasins across all over the basin and calibrate all those at the same time. This is what I call global strategy, and this is how it's shown basically. And then I validate it at different subbasins that I didn't use in my calibration. For individual, I'll do basically on a land cover basis. So for example, if this basin is covered close to 100 by crop, I calibrate this and validate it in another basins that are also crop dominated, or use basically the same parameters. I'll just pass this and do the same thing, but the results were published in my paper. That was a paper actually I did during my PhD studies, calibrating mesh for the Great Lakes Basin. So we found a global strategy in which we do all the basins, or many basins at the same time simultaneously, and then validate it at different places is a preferred method. And we were able to actually really get very good hydrographs using this calibration strategy. This paper was sort of is now considered a baseline calibration study in that area, and other projects are now using the results. Finishing up with some works in progress. So basically, now within the Global Institute for Water Security, there is a big team working on not only developing mesh, but also applying it in various major basins within Canada. And the idea is to be able to, at least at some point, do all the major basins with mesh at some point. So the one that I showed you was Great Lakes area here. Currently, we are also doing the Mackenzie Basin, very northern part of Canada. This one is about 1.8 million kilometers squared, so fairly large compared to the basins you have here in Europe, I guess. And also this Nelson Churchill is another one, which is again 1 million kilometers squared. We are also applying mesh to that one. And like I said, we are moving towards applying mesh, not only improving mesh in terms of its ability to capture different processes, but also to actually apply it in very large basins in Canada. This is some of the, again, multi-criteria sensitivity analysis that I showed you, and then a multi-criteria calibration of mesh for major basins. You might get a different answer if you choose iOS 30. You might get a different answer. Of course, depending on your modeling application, the differences could be lower or higher, basically. But long story short, I rely on VARS to give me information across all the scales and use that information.
I was thinking maybe if you're, depending on what calibration algorithm you use, it might be that the algorithm has a tendency to take steps of a certain size. In which case you might be able to kind of match up. I don't know, to what extent that is sensible or not, but.
Yeah, exactly. That's a very good point. Yeah, but we normally tend to use what's called the global search algorithms. I didn't present any specific algorithms, but I use what's called DDS, dynamically dimension search algorithm, which is a it's not a derivative-based algorithm that could be sensitive to the step size. It's categorized as a global search algorithm that tends to explore the entire parameter space. So, but you're right. Depending on if you use a certain algorithm, the usefulness of your sensitivity analysis could be limited. Okay?
Okay, I think
Time for lunch?
So let's thank Amin and Sarah one more time. It's very interesting. I think everyone's enjoyed it. I just mentioned that I don't know if we have any spaces left, but we're doing a sensitivity analysis training. Is it June? Last week of June. Yeah. So we start very simple and try to build up a bit. 2 days last week of June, in case anyone wants to know more about this kind of stuff.